Welcome. Please take a seat.
Okay.
Mr. Candidate, you confront a committee which was appointed by the Council of Deans and that is charged with the task of examining both your dissertation and the propositions submitted therewith. Professor Siebes will open the examination. Please, go ahead.
Dank u wel, meneer de rector. Meneer de kandidaat, Mr. Candidate, it was a pleasure to read your thesis. It was a bit like a trip through memory lane because subgroup discovery was one of the first topics I worked on a bit. And we did this, for example, in a European project. And in European projects, you have project officers and reviewers. And one of the reviewers was a statistician. And the statistician had very clear ideas about what subgroup discovery should do or should not do. And perhaps not surprising, he did not agree with you. He said that a subgroup, you should look whether or not it deviates from the rest of the distribution, from the rest of the data set, because otherwise you are comparing an object with itself. So I had long discussions with him, but what I'm curious about is would your answer to the statistician be?
Ongeleerde opponent. Thank you for your question. I mean, it's a big debate about subgroup discovery, what it is and what it isn't, and it has been many years of discussions that people don't really believe that it exists at all. But in this case, precisely, I think as the population of the data is made by its parts, we should also consider the subgroup to be one of its parts. And so I would never consider it as the opposite of the subgroup, just the negative set. So I would consider it to be part. I understand what his problem, where his problem comes from, because then we are talking about the sampling distribution, and it comes from there too. Yeah, but that's other issues.
So you use it as one of the ways to distinguish subgroup discovery from classification.
Yeah.
And I was wondering, isn't it that if you're doing subgroup discovery, you're not so much interested in the whole data set, but only in some parts that are really different, so that you would not necessarily make a list that covers everything. It's like, okay, these two subgroups are interesting, and the rest, blah, it's average. And if you do it like that, then you don't need your final rule, your default rule, because you simply say, yeah, the rest is not that interesting. Would this fit in the way you approach subgroup discovery in your thesis?
Yeah, thank you for your question. So the default rule is more like, in this case for subgroup discovery, is more like an artifact. It's there to cover what is not covered. And if we say that the default rule already covers what is not interesting, then all the subgroups only represent what is interesting. And so it doesn't need to be well covered by the subgroups itself. And so in this case, I would say the default rule is a crucial part of this method. I extend it to many rules, but that's mostly a theoretical result. Because if you're interested in less subgroups, you can find less. You can find with different quality measures. And so, yeah, it depends of what the user wants to find in the end. I think it's very subjective.
Okay, okay. Then the other distinction between classification rules and subgroup discovery is the quality measure that you define in chapter 2. I stay in chapter 2. I know that gives you the feeling he didn't read more. I did, but somehow chapter 2 really intrigues me. And I was wondering whether the two quality measures you mentioned there, so on the one hand, your accuracy in whatever way you want to define it, and on the other hand, this weighted KL distance, my feeling is that the two are actually pretty much the same. Because the only way you can get a big KL distance is if the distribution of your population that you define with your subgroup has a peak where the original distribution doesn't. You really have to have a different probability there to get this distance. So I was wondering whether or not this is not simply the reason that subgroup discovery rules and classification rules are very much similar.
Yeah, it depends. In certain data sets, I would say yes. In others, no. I mean, the question here is that in rule learning for prediction, you tend to find models that cover well homogeneously certain parts of the data. So you want to find a partition of the data that in every part it's very homogeneous. While in subgroup discovery, that's also in a sense the quality of the measure, but it doesn't really matter in that sense. So for example, if you look at the numeric case, the way we measure the distribution or the targets, it's both by a normal distribution with mean and standard deviation. So a good subgroup can just be a different mean that is far away, but maybe it has a big standard deviation. Or it can be a good subgroup that has a small standard deviation and it's close by to the mean of the data set. So in that sense, subgroup discovery is about exploring things that are different. And a lot of the times, because they describe well their subsets, they are good for prediction. It doesn't have to be the case.
So if you restrict ourselves to the 0,1 dependent variable, though you don't have this excuse of, well, you could look at sigma, we only have a mean. Would there then be a difference?
I mean, there would also be a difference, but it's smaller because also how the distribution can change is only by the counts of 0, 1. So there's less ways you can find different well-describing. But you always have the example of, I mean, the data set is, let's say, very imbalanced for one side, and you just find something that is maybe not very good predictive, is 50-50 for each class. And it can be interesting still from a subgroup discovery perspective, because you are saying, for example, yeah, people that buy bread on average, they just buy beer 50-50 compared with the population that buys a lot. And so you can still find things, but because there's less ranges for the Bernoulli distribution to be interesting, there's less opportunities to find subgroups there, I would say.
Okay. And then this KL distance is not symmetric. It's not a metric. So people usually take, let's say, the sum of the two KL distances with the distribution switched. You only take one. Why are the other type of dissimilarities not interesting for a subgroup?
They could be, but in this case, we're always measuring them from the data perspective. How much more would it cost us to describe it with the data set distribution in terms of bits? So in this case, we're only concerned with subgroups that are better described by themselves, by their distribution, than by the data set distribution. And it arises also naturally from our formulation with MDL. So yeah, those are the two reasons.
So given that I still have some time, I'm going to prove that I read more. I also have a question about page 64, I think, from the top of my head. It's about you want to throw out candidates that are duplicates in some sense of others. And what you do there is you actually take the opposite of the closure of an item set where you take the largest one,
Yeah.
but you take the smallest one. But then I was thinking, the closure, that's unique. If you take the largest one, there is a unique choice. But if you say, no, we don't take the closure itself, but one of its generators, then one closed set can have many generators.
Yeah.
How do you choose between the generators? Because this doesn't sound to be, you have to do something arbitrary there. What do you do?
Indeed, I do a lexicographic. I choose them by order that they appear. But I mean, from the perspective of the length of the model, we would prefer the ones that are smaller, so the generators to them. But it makes sense that the closure, yeah.
Okay, thank you very much. Dank u wel, meneer de rector.
Thank you, Professor Siebes, for your contribution and for coming from the University of Utrecht to Leiden. Thank you. The examination shall be continued by Professor Vreeken, Saarland University in Denmark. Please take the floor.
Dank u, meneer de rector. Meneer de kandidaat, Mr. Candidate, I also enjoyed very much reading your dissertation, and also for me it was a trip down memory lane. Not so much because I worked on subgroup discovery, dabbled a little bit with this, but particularly because you focus on using the MDL principle to sort out a lot of problems that we have in pattern mining. And hence, it was a very interesting dissertation for me to read. You specify in chapters 4 and 5 for the CLASSI and the RSD algorithm 3 main desiderata. You want to reduce redundancy, right, in the output set. You want to be able to have an algorithm that is effective and efficient. We have only finite time to bother finding these patterns. And the third one is not so much my trip down memory lane, but one of my current main research interests, namely statistical guarantees. And while reading your dissertation, I was left with a number of questions in this regard. Because there's many possible guarantees one can give. And, so I would like to invite one of your paranymphs, whoever takes the, the opportunity, to read out proposition number 2.
MDL for point hypothesis selection can be interpreted as the goodness of fit plus a penalty for multiple hypothesis testing. The goodness of fit is given by the maximum likelihood estimate and the multiple hypothesis testing by model complexity, which in practice counts all possible models with a minimum number of assumptions.
Thank you very much. Okay, let's agree on the first part. The likelihood, the goodness of fit, I totally agree with. The second part, I have, say, there's some room for convincing left. You write that it takes into account the model space, but multiple hypothesis testing, the name kind of implies that we look at how many tests do we perform. So could you please elaborate a little bit further on how you take into account how many tests you actually perform? How often do you look at the data, and how do you incorporate this within your selection criterion?
So, hooggeleerde opponents, thank you for your question. So, indeed, it's not many people interpret it directly as multiple hypothesis testing, but as the way we defined the model complexity over the space of all possible models, we are in a sense counting all the possible models. And the fact that we use priors or codes in MDL that are uniform, so they give more or less the same weight, or the universal code of integers, which more or less tries to do the log n with a small penalty. What we're indeed doing is we are counting the models and then we're giving a weight. And now we are seeing it from code, so we are summing it up. But if we see it from probabilities, we're basically dividing by the number of models that exist. We're multiplying by it. And if we look at the simplest way of multiple hypothesis testing, such as Bonferroni, we are dividing by the number of hypotheses that we are actually testing. And so in a sense, we are giving a penalty that we look at more models. And it is, in a sense, similar to the frequencist approach of multiple hypothesis testing. Yeah, in that sense, I would say.
Okay. There's still some room for convincing left to be done. Let's take a step back. Whenever we have a project that involves any domain experts, particularly people from the medical domain, they love guarantees. They love statistical guarantees and they love p-values. colleague, Professor Grünwald, is cringing right now, I mean, and rightly so, but in many domains, p-values are king. Let's take a look at, let's reinterpret the score that you define and that you work with. Would it be possible to interpret in any which way the gaining compression that you get as if it's a p-value, such that we can set, before we start our entire discovery, some alpha, some threshold alpha, before we look at the data, and then can find a model that would satisfy our domain experts, because they don't believe in MDL, sadly.
Indeed, I think that's true, and I have been advocating for it, but I haven't explicitly said it in my thesis. I mean, as we can see the model gain as a base factor, we can look at the interpretation from Jeffries, where he mentions that if you have a base factor of above 1, it's in favor of the alternative hypothesis. If it's 10, it's kind of strong, and if it's 100, it's quite strong. And so you could, in a sense, develop a system like this, which would be similar to the alpha values, but slightly different. And then with the multiple hypothesis testing, you would divide the alpha by that penalty, in a sense. Yeah.
Indeed, indeed. I agree with a large part of your interpretation. However, Bonferroni correction, I mean, statistically sound and very nice on paper. In practice, especially when you apply it to pattern mining, is frankly completely useless. In the hypothesis space, the number of tests that we want to perform was exponential. So we have to divide alpha by a ridiculously large number, and in practice, alpha 0, I mean, it's almost impossible to attain any significance on the data. So there, the Bonferroni approach, and hence your interpretation, I have very strong doubts that it would work directly. These days, I'm very interested in sequential hypothesis testing, where we take into account, we start from a basic threshold, right? I mean, you could interpret the delta that you have in your model cost as such an, basically the cost, the p-value in a way, the difference between the model cost and the data gain as such a p-value. But then we would like to adapt dynamically the threshold of how many bits should we gain per iteration. Could you share a few thoughts on how we could do that within your algorithm? Your algorithm is sequential. It adds patterns one by one. In your current code, the model cost is the same. So the penalty that we incur by adding something is the same for the first iteration as it is for the last iteration. Hence, I was wondering, on the multiple hypothesis testing interpretation, do we have such a sequential viewpoint that we could take that would help me to convince my domain experts?
Thank you for your question. I also have been thinking about it a lot, actually. And I thought about if we could actually do it in a way. And yes, but I would say for this type of work is more an algorithmic choice. So in this type of work, the iteration is more as an algorithmic procedure to find the models, but you could always constrain finding the next rules on the previous ones, and thus change the model complexity and the data complexity if it would be related with that too, I would say.
Okay, good. Yep. We're getting closer to where I want to be. Let's take a look at one of your algorithms, and let's take the classic algorithm, which generates lots of candidates beforehand and then starts to sift through them, looking at them, well, all of them in every iteration, basically all the time. What would you say is the risk for overfitting within the classic algorithm?
I would say that there's not so much risk for overfitting. Actually, I think our penalties are we're over conservative in many of the things we actually do.
Could you elaborate on that?
So for example, some of the codes we do, so especially from the classy perspective, which uses an old encoding for some related work that we actually didn't develop. So for example, from the items perspective, we could also, if we find 3 items together for a pattern, we could actually change the codes as we find them, so that if there are 3, it can be a combination, which will be more optimal. Also, when we say the number of rules or the number of patterns that exist, we let the code go until infinity, but we could actually restrict it to the number of possible patterns or to the number of possible rules that we know it would be possible to find in the maximum sense, an upper bound. And we don't do that. So we count all models, we count the distributions, but we don't, but we are even counting more models than exist.
Okay, one final question, if I may. The short one, yes. Suppose that, so indeed the encoding is not as efficient as it could be, so we incur a higher penalty. However, later on in the search process, I'm quite confident you will add candidates which maybe add an overall gain in bits of 0.1 bits or something like this, or even less. Would you consider such a pattern significant, or would you consider it overfitting?
Yeah, thank you for the question. So in this case, I still consider that they are not overfitting. I mean, we use a normalized gain, so it's the gain over the number of samples it covers. So we are benefiting patterns that cover less. So they are not the most significant. They are the most significant per instance. And independently of dividing or not by the number of instances, if the gain is above 1, we know that there's more evidence in favor of that rule than not. So in a sense, they are significant, but yeah, there's more evidence in favor.
Let's agree on significant. Thank you very much.
Thank you, Professor Vreeken. The examination shall now be continued by Professor Grünwald. Please take the floor.
Just a moment. Meneer de kandidaat, I have read your thesis with great interest, but of course it also raises interesting issues that we can now discuss. And I also, yes, I have to start with chapter 2 because early on I found something very intriguing. When you basically decide that whenever a variable is numerical, you code it as if it would be normally distributed. And you write about that. For numeric targets, other distributions could have been chosen. However, the normal distribution incorporates some of the most relevant information of the data through the mean and the variance of the data. And this made me wonder several things. The first question is, if this is what you're after, why don't you just code the mean and the variance of the data?
Geleerd opponent. So why don't I just cover? Can you rephrase the question?
So you say you act as if numeric targets are normally distributed.
Yeah.
And one of the main reasons for doing that is that what you then describe gives you a lot of information about the data because you describe the mean and the variance of the data. So then my question is, why don't you even talk about normal distributions? Why don't you just say, for numeric targets, we describe them in terms of their mean and their variance?
Oh, yes. No, indeed. I mean, as we only use normal distributions, we describe both the default and the data sets by the mean and the deviance. And then we also used, for describing each subgroup, also we only use the mean and we describe by the statistics.
But then could you not tell the whole story of chapter 2 and in fact also later chapters without referring to the normal distribution?
I mean, I could use other distributions indeed, but in this case, as it was a first approach, we decided to use the normal as it's the most standard and it has some robust properties. And if there's some violations of that, of the fact that it's normal, so that's why we decided to use. But we would like to, in the future, to use other distributions, such as the empirical distribution would be the best. But yeah.
But yeah, you said you said it has some robustness properties, but that is in fact what I'm worried about. Is it so robust? If you think about outliers, for example.
In terms of outliers, no. Because of I mean, as it's the mean, the median, for example, has much better properties in relation to outliers than the mean. The mean is pushed by the outliers, and we actually see that in a lot of the results from chapter 5, I think, from the RSD. And when we are looking at the distributions, for example, from the hotels and from the flights, because of the tails, the means are actually quite pushed to some side.
Right, right.
And so in that sense, it's not as robust, but it would also be much more complicated to do it with other distributions.
In fact, I wonder, is it much more complicated because what you really are doing is you are, if you think of it in two-part codes, of course, then you do it in a more advanced way, but in two-part codes, you're recording basically the mean, and then you're recording deviations from the mean.
Yeah.
And now you would record the median and then deviations from the median using a code which is proportional to the absolute distance rather than the squared distance. Is that much more complicated?
I mean, as I look directly just at what you said, I would say no. But thinking of passing the integral of the Bayesian priors over the median, I would say it would probably be slightly more complicated.
Yes, I agree. But I wonder, of course, I very much like that you use these advanced methods because I've been working on them for the last 20 years. But on the other hand, maybe if you use just a two-part code, it's easy, and maybe you gain more than you lose.
No, it would be possible, and it would be an interesting approach, yeah.
Okay, and I have another question on this, and that is, how realistic is it even in general to assume that your errors are normally distributed, apart from robustness? Because you're working with, I mean, if you had like one random variable, okay, that's normal, that we see that all the time in nature, but you have all these rule lists. So you say, if the pattern is in this small subset, then this is normal. Is that a realistic thing to assume?
It depends. It depends of the data in itself. We can see it also, I mean, of course, the model that generated the data doesn't have to be included, but we see from different times, for example, with decision trees and with rule lists, that if the data was generated by linear regression, maybe, with a decision tree, it kind of awkwardly partitions the data in a not so nice way. So if the data has a model generation that is quite different than the format of a rule list, no, it wouldn't be appropriate.
Yeah, that's I have actually come to the same conclusion that, but regression does seem like a more or less realistic way in which data might have been generated, and it's exactly then that you get in trouble. Yeah, what are your comments on that?
I mean, indeed, the ideal approach would be to be more flexible on the distributions and also on the patterns. I mean, at this moment, the patterns are very rigid, so they are patterns,
right? Yeah.
And they create a little box in the data. But I mean, if we would have another generation process or more flexible distributions, it could accommodate more things. Yeah. So if you could choose at the time, which would be the best distribution to cover the data?
Right.
Yeah.
But then, of course, you have the problem that there are many choices you can now.
Yes, and I went for the simplest choice.
Yeah. Okay, I have also a quite different question about section 3.7, if I'm still allowed. That's about the theoretical difference between subgroup list and predictive rule list. And this is a topic that has implicitly also occurred before in this defense. And so I agree with the analysis there in the case that you're comparing, you fix the number of rules. Let's say there are 4 rules, and then you try to find the optimal rules according to the 2 different criteria. You will get something different. But what if, I keep wondering, if you compare a fixed number, let's say 4, for the predictive rule list, and then one more for the subgroup list, wouldn't many optimality criteria drive you to end up with the same thing after all, where the fifth one is basically empty? So in the subgroup list, you get one extra rule which covers all negative cases from the predictive rule list. And then you end up with the default rule, which is now, well, it's a nice default rule, but it's never applied anymore.
Yeah, indeed that could happen. But the question here also, there's another problem there that we didn't come up with, which is that, okay, the algorithm is also biased for a certain type of rules that we are finding. So the algorithm also biases what we find. I think if we would look at it from an optimality perspective, and we would find the optimal predictive rule lists and the optimal subgroup lists, they would be different. But also because of how we do the greedy approach and we add it one at a time, I think a lot of times we could get to that problem, yes, especially for a binary case.
Okay, thank you.
Thank you, Professor Grünwald. The examination shall now be continued by Professor Mentens, who will join us online. Can you hear us?
Yes, can you hear me?
Welcome, please go ahead.
Yeah. Dear Mr. Candidate, I also enjoyed reading your dissertation, and I learned a lot actually, because the topic is not really my field of expertise. I rather work on security, actually embedded security. So my questions will be a bit less detailed and rather a bit broader. So first question is related to security. So a typical use case of machine learning in security is network intrusion detection, where the goal is to detect anomalies in network traffic compared to what the system believes to see as benign or normal traffic. For example, to detect distributed denial of service attacks. So advanced intrusion detection systems also make use of online learning, where the model is constantly retrained every short period of time, for example, every few minutes. Can you elaborate to which extent the results of your work can be applied to this scenario of anomaly detection and using online learning to retrain the model, for instance?
Hooggeleerde opponents, thank you for your question. Yes, I mean, as you said, we want to find traffic that is different from normal, and that's what we try to, in a sense, do here with this work. The work we did centers more on a fixed setting, so the data is already fixed and we look at it. From an active learning, the way we construct our models is not the best. So rule lists have certain problems for active learning, as they are completely fixed in an ordered way. And so if, for example, one rule becomes spurious and we don't want to use it anymore, it's hard to disentangle it from the rest. I would say rule sets would be more appropriate for that case, where you could interpret them semi-independently and then remove them when they wouldn't be active, or learn more when they would be better, yeah.
Second question is related to embedded or edge computing. So there is a trend for some applications to move machine learning to the edge. So to run machine learning algorithms in edge computing devices that are typically more constrained than traditional servers or clusters. So the energy budget of these edge devices and computational power or more constrained. Can you comment to which extent your work can contribute to this shift towards edge computing?
Thank you for your question. I mean, in a sense, the rule lists are very light models. The maximum you would have to spend time looking at conditions if they are met or not for each instance of the data. And of course, if it would be a rule that is activated at the end, you have to look at more rules. But in a sense, they are kind of light models if we compare them with deep learning. And we hope that the robust properties that we embedded our models with would contribute to be more robust, and that they would be continue being valid after some time. Yeah.
Okay, interesting. Thank you. And then a last question. So assume somebody wants to invest in a startup company to valorize the results of your work. So which particular part of your work would have the highest potential for commercialization and why?
I think in my work, what I personally find more interesting and sub-explored would be the part of statistically robust subgroup discovery. First, because it's not a very hot topic at the moment. And I think a lot of people don't use it because they don't know what it is. And it's a good initial step to actually learn more about the data and to explore the data. A lot of the problems it has nowadays is that maybe we cannot trust the rules we find because they are not robust or they are spurious. And so in a sense, I think it's a nice idea before actually looking at the data to just look at what are the subsets that are different and if they make sense and why are they different, and looking at these different perspectives of the data. And I think that's the most important part. It's an undervalued step in the data mining process and in machine learning, but I think it's actually one of the most relevant and that actually defines success later on.
Okay, thank you. Those were my questions.
Thank you, Professor Mentens. This examination shall be continued by Professor Plaat.
Geachte rector, hartelijk dank dat u mij de mogelijkheid geeft oppositie te voeren in deze vergadering. Geachte kandidaat, I very much enjoyed reading your thesis. It reminded me of a long time ago when expert systems were all the rage in artificial intelligence. They were one of the big successes, or so people thought about 50 years ago. And actually they were successful to a certain extent, but the rules that these expert systems were using were based on human experts. And it turned out that there were some problems with getting the knowledge out of the brains and minds of the human experts. Your work is much better. Your work is based on real data. It reminds me that there is a thing in between expert systems and your work, and that is deep learning, which was also very successful. So I was wondering, you're getting your rules out of the data, which is wonderful, directly out of the data. Could you describe to us, based on your algorithms that you've been using to get your rules out of the data, how you could derive rules out of a neural network or a deep learning system?
Geleerde opponent, thank you for your question. So how could we take them out of a deep learning system? I mean, it depends. So if you want to just explain the deep learning system, there's now the local approaches for explainability, where you sample different instances or around different instances. You find how they are distributed locally, and then you can fit a model to this new data. And you can simulate, in a way, what is there. Or you can try to simulate the deep learning model by directly taking their inputs and outputs and trying to find. But then we are not mimicking the data, we are mimicking the deep learning.
Which is exactly what I would like you to do. So do you think you could use the minimum description length approach for deriving knowledge out of the weights of the neurons of the neural network?
I think it's possible because a lot of the times we have very big deep neural networks, but as it was proved, most of the neurons are not doing much for the predictions. So in a sense, there's a minimum number of neurons that are actually important for that predictions. Of course, the rule-based models would have smaller capacity because they cannot mimic the same nonlinear relationships as deep learning. But I think for certain data sets, they could mimic with a certain error level deep learning.
So in a sense, you're talking about compression of all these weights, all these very large and deep neural networks.
Yes.
Okay, thank you very much. I would like to make a step to one of your propositions, and I would like to ask one of your paronyms to please read it. This is the shortest proposition that you've included, and I really like the elegance of this proposition. Do you know which proposition I'm talking about?
Either 3 or 10.
It's number 3, indeed.
An approximate solution to an exact problem can be better than an exact solution to an approximate problem.
You were speaking quite fast, Mr. Paranymph. It was almost impossible to hear the nuance, so the candidate, Mr. Candidate, is comparing exact versus approximate solutions and then using approximate against exact. Can you please explain to us how you're trying to confuse us in a very beautiful and elegant way?
Thank you for your question. Indeed, this was a problem that I found while I was comparing with other state-of-the-art approaches. And the question is that sometimes we have more or less an exact mathematical problem, and we have more than 2 approaches, but let's say we only have 2 approaches here. And one is to have an approximate solution, so an algorithm that tries to approximate it. So the algorithm is not optimal, doesn't find the optimal, but tries to approximate it directly, the mathematical objective. And the other way is that you simplify the problem and then you try to find an optimal solution.
So you're saying that an approximate solution can be better and more useful than an exact solution? That sounds like a contradiction.
Yeah, but for I mean, in the end, they are both approximates, because when you are simplifying the problem and then you find an optimal solution in this sub-problem, so if you see a diagram of all the possible solutions, the exact solution is going to be in a small set, and it finds an optimal solution in a smaller set. If this smaller set is good, or is where the optimal is, that's good. If not, it will never find it. So it will always be stuck to this. And that's, I mean, one of the things we found, we compared with methods that would find optimal solutions, but they would approximate the problem. So instead of going through all the rules or almost all the possible rules, they would find a subset of the rules, smaller, so around 1,000, and then would try to find a solution, an optimal solution there, while we would go for millions or 10 millions of rules and then find an approximate solution there. And what we find a lot of times is that we'd get better solutions there because the other model would never be able to find it.
I think I heard you correctly, but I am checking. So you're saying that exact solutions are approximate?
An exact solution to an approximate problem is an approximate solution.
Okay. There is a chance that you will be a doctor of philosophy at the end of this, so which might be very appropriate if that would occur. Yes, I would like to go to another proposition, if there's time, which is proposition 5. I will tell you right away which number it is. Can you please read proposition 5?
Interpretability is a personal or community-related property. Interpretability is a domain-specific notion, so there cannot be an all-purpose definition. Usually, however, an interpretable machine learning model is constrained in model form so that it's either useful to someone or obeys structural knowledge of domain, or physical constraints that come from domain knowledge.
It sounds as if this one is related to your explanation of proposition number 3, as that you cannot have your cake and eat it too. Either the interpretable machine learning model is useful for the user, or it's very close to the structure of the problem. Am I reading you correctly here?
Ora est.
Mr. Candidate, the time allotted to the examination of your dissertation and its propositions has passed. The committee will now withdraw in order to deliberate. I request that you and your company await our return here.
Neem plaats.
Mr. Candidate, we have examined your dissertation and the propositions appended thereto. We have heard your defense and we have considered the report of the faculty concerning your previous studies. On the basis of this, we have decided to admit you to the doctorate. Professor Bäck is empowered to confer the dignity upon you in the customary fashion.
Volgane aanvaard ik de taak mij door de rector magnificus der Universiteit opgedragen. Uit kracht dan van de bevoegdheid ons bij wet toegekend volgens het besluit van de commissie, hier tegenwoordig, verklaar ik bij deze u, Hugo Manuel Proença, te bevorderen tot doctor. Ten bewijze hiervan zal u het diploma door rector, secretaris en promotor ondertekend en met het grootzegel der universiteit bevestigd ter hand worden gesteld.
Neem plaats.
Having completed the duty assigned to me, may I be the first to address you as Dr. Hugo and to congratulate you on the award of the dignity you have obtained. This honorable distinction is a well-deserved and highly valued privilege. At the same time, you are called upon never to lose sight of the obligations it imposes on you in the name of science and society.
Dear Dr. Proença, dear Hugo, in the acknowledgements of your thesis, you wrote that my guidance helped you traverse the sinuous paths of research, and these paths are so nicely illustrated on the cover of this thesis. And I can only imagine that here we see Hugo walking towards the horizon with his backpack. And it makes you also wonder, where did this man come from? And it was also a sinuous path before, because he was born in Hong Kong, lived in Macau, in Lisbon, did internships in Jiangsu, China, in Prague in Czech Republic. And did he do a master or bachelor in computer science? No, in mechanical engineering. But then he went to Leiden to do a PhD in computer science. And he worked on the CISPA project, which was a collaboration with IIT Roorkee in India and with GE Aviation also in India. And this meant that also traveling was involved, which Hugo likes very much. And he went there, he enjoys India a lot. And much later I also went there, and I now understand why he enjoys it so much there. The PhD then, the first year, was really overwhelming. You came from mechanical engineering, but you had to learn so much computer science stuff. Pattern mining was new, there was MDL, there was programming involved. So overwhelming. And having lived and traveled in many countries, you are very social and easygoing, but also you have quite high expectations from yourself. And at some point in, I think, the start of the second year, I took some coaching sessions, and part of this was a conversation with the coach and with you. And at that point, we found out that you were actually quite stressed, because you find it hard to ask me questions, because you thought you had to come up with the answers yourself first. And also you were uncertain of what I thought of you, which made you also a bit uncertain. So I'm still very thankful for you for openly discussing this with me, because one, it helped me learn as a supervisor, as your advisor, but also I think it helped us a lot, and I think over the years we managed to do very well. Meanwhile, the sinuous paths of research continued, and already very soon, within half a year after starting, you had a topic you would like to do, supervised MDL. And I warned you a little bit about this because I said, well, classification, there's so much related work on this, publishing will be hard. But okay, you said, I want to do this, and I supported that, and this resulted in a very good manuscript, which unfortunately was rejected many, many times. In the end, though, it has been published, and we changed the focus from classification to subgroup discovery to have this unified picture that we saw today also in the discussion. And this was a very good move because you quickly had a new conference paper, and now we have this additional journal paper in revision, which is very nice. So in the end, we have a very robust thesis on robust rules. And not so long ago, when you were still working on the thesis, you came to me and you said, well, I read some text that I wrote a few years, and I must say, I have learned a lot. So thank you, Matthijs. And yes, Hugo, you have learned a lot on many aspects of science and beyond, which I think is what doing a PhD is all about. And no, you should not thank me, but yourself for persevering, for keeping believing in your ideas, and for making it to where you stand today. Dr. Proença, it's an honor for me to congratulate you here from this position, also to your family and friends, your partner who recently also defended PhD. You're leaving academia, at least for the time being, and I wish you good luck with your career. I'm looking forward to following your path in the future. I hope it will still include research, and I hope it will be appropriately sinuous. As a present later, I will get you a book from Haruki Murakami, one of my favorite authors, who is exceptionally good at telling stories that follow sinuous paths. I hope it will inspire you.
Thank you. It's an agreeable duty for me, very learned sir, to congratulate you upon your degree, also on behalf of the University and its Council of Deans. And herewith I declare this ceremony closed. Before we go, I would like to give Professor Mentens the opportunity, because she is online and she cannot join us in congratulating you, for a brief congratulation.
Yeah, congratulations. Oh, I didn't expect this, so congratulations. Yeah. But yes, congratulations on a very nice dissertation and very nice work, and I wish you all the best in the future. So.
Okay, thank you. And you all, thank you for being here, and now it's really closed.
Applaus maar.